material, right? That's the whole point. So how do I find F? Just do the static force analysis. In order to do so, you isolate first. So isolate them. One is right here. The other one is goes like this. So if you just apply the static load on this guy, you have 100 newtons. And then when you grip this grip right there, areas, you're gonna start developing a force by what? The material, the part that you have on this tip. So that will cause the force like this. Here's the force right there. And then there's the pin right in the middle. So either way is fine, but let me just go with the one of them. Let's get rid of this. And then some force will start developing right here. So I'm going to say this is Fp. And this is also the F of object, from object. There are three components, right? So all I need is to find out Fp. This is basically the same force that I want for the tau actual, correct? So how do I do? Well, this is the best thing is that because I need to know this, best equation that to find out the Fp should be the sigma m, maybe at O, right? Clockwise positive is equal to 0. Correct? So so that means that the 100 times the total distance, which is 145, minus plus Fp. Fp times how much? 45. That is equal to 0. So whatever Fp goes into this, and then this will give you the S1, right? Okay, so that's the really quick review on the test. So again, as I said, if the class average is below 70, say 60 for example, then I'll give you a chance to make up on Friday with one of those problems in test. I don't know which one I'm going to choose, but one of those problems. So try to master this at home if you didn't have a chance to.
It would be a problem that we've seen before.
Huh?
It would be a problem that we've seen before.
Any problems out of these 4 problems?
Oh, okay.
So I'm going to just choose one of those problems to test, whichever problem. And then I'll let you guys solve it again, just to add on your test number 1, if class average is below 70. Hopefully it is more than 70, so we don't have to do the makeup. We'll see. The GA didn't finish the grading yet, so. All right? Oh, okay, so I'm going to move on to the next. Google. So here's homework. Okay, so I think we're going to move on to the chapter 4. Torsional shear stress. So now we'll start working on the torsional shear stress, which is a little bit different from the pure shear stress. It's a little bit different, and then we'll see what's the difference. But basic idea is the same. We actually start with the design shear stress, and then actual shear stress, and then limit those to actual shear stress with design shear stress. Design process is the same, but the way that we actually calculate the actual shear stress is a little different. So we'll discuss about the theory behind it to find out the shear stress, okay? Before we actually do the shear stress analysis, let's just start with the little bit of the review quick on the torsional case. I'm sure that everyone had a chance to look at the moment, but moment is the same as the torque in this case. So the torque here is coming from, if you have a system like this with the force acting on it, and then if you know the distance, the shortest distance has to be shortest distance, then torque is defined by torque times distance, right? That's basic physics. Force times distance. That's the torque. And then if you, by using simple, this is F times V. And usually metric. Simply we start with this equation to find torque. And then because we are focusing on torsional shear stress, we need to be able to find torque first. Evaluate the torque, and then the torque will give you the maximum shear stress. Okay? And then sometimes problems describe the power instead of torque, which is the torque times. What is torque times? What is the power? Torque times rotational speed, right? That's the power. Sometimes they might give you power to find the stress. So you need to know the relationship between the power and torque. And then the power, usually P, simple P is going to be T, torque times M, which is the rotational speed. Wait down for a second. Okay. And then if it is go one step further, then they might give you energy. Energy, which is power times time. How much of power for how long? That's your energy. So we use joule, J. Power is watt in general, and times T. So watt times time second is going to be your joule. And then when it comes to the industrial application, people use the term RPM. RPM as a revolutionary speed, the rotational speed. Sometimes they might give you the power and then the speed to find torque. And then once you know the torque, then you can find stress. But if the RPM is given, the first thing is that in order to find this torque, you need to convert this RPM to the radian per second, right? So how do I change it? Well, our RPM is in radian per second. RPM is nothing more than revolution per minute, right? That's RPM. So in order to change that RPM to the radian per second, you take care of all this and change it to the unit that you want, radian per second. How do I change it? Well, minute, in order to cancel 1 minute, 1 minute is 60 seconds. And then one revolution to radian per second, radian. What is one revolution in radian? 2 pi. Right? So ending up multiplying 2 pi over 60. That's your radian per second. So whenever you see RPM, just multiply 2 pi over 60. 2 pi over 60 to get your radian per second. And then once you have that, the speed in radian per second goes into this equation to find T, torque T. Okay? Newton meter torque T. So for example, so that if you see 1750 RPM, that should be equal to 750 times, simply is 2 pi over 60, that's 183. That's easy calculation. So there's a one problem in the textbook. Ask us to find the torque. Again, these type of problem will not show up in the test, but this is kind of one of the examples that you have to know, understand, to find the stress later. So let's say you have a torque. Torque is given a torque. Trying to find torque. If you collect all the given data right there, it should be power, 95 kilowatts, and then the RPM is given 525 RPM, 525. It's not radian per second, but need to change it to the radian per second to find torque. So how to find it? Of course, we need to get the torque T, which is coming from P over N. Power is given right there, 95,000. And then your RPM is coming from this equation right here, 2 pi over 60. So 525 over 60. That's your torque T. So that's this whole thing is the 55 radian per second. So actual torque is going to be 1,727 Newton. Okay, so that's how this basically is a typical questions to evaluate the stress, which is going to be evaluating torque first from the power and then RPM in general, and then from the torque, then you can actually evaluate the stress later on. Okay, that's how you do it. Okay, but sometimes you need to work out with the US customers. So let's just talk a little bit about the US customers before we start developing the stress equation, torsional shear stress. So in US customary, torque and power, the torque T. Use the same symbol with the pound inch. And then N here is going to be speed. Usually we use RPM for in the US. And then the P, power, is usually horsepower. Or sometimes you will see HP, horsepower. And then in order to convert the 1 horsepower, you probably remember 6,600. This is 6,600 pound inch per second. That's the power, the horsepower and power relationship. And once you have the horsepower, 1 horsepower is going to be T times N. T is the torque pound inch times N, which is RPM, divided by 63,000. Okay, so 63,000. This guy is coming from 66 times 60. It's backward from radian to the RPM. So one example there is if you have a torque T of 15,000 pound inch, and then speed is given as RPM. Okay. Then your horsepower will be 15,000 times 525. Just straight solution, substitution for the equation, divided by 63,000. That's your horsepower. That's how you find horsepower. Sometimes you will see you have to go back and forth between the. But our terminal goal is to find this torque T. You evaluate torque T because the torque T is torque is basically the one that will cause the stress, shear stress in the torsional case. Okay, so either way, you need to be able to evaluate torque T to be able to find the stress. Okay, once I have stress, I can design the shaft. This is mostly for the shaft design in general, but this is just general case, and then specific shaft design. The particular shaft design is going to be dealt in the solid mechanics, right? So let's just talk a little bit about the. I think we still have time, so a little bit about the stress case and how the stress is developing in the rotational members like a shaft. So torsional. Shear stress. How do we evaluate torsional shear stress for a given torque T? Okay. So let's just think about a member like a shaft, where your torque is applied both ends. Okay. And then in order to see how the torque is going to be, the stress is going to be developed in there on this shaft, we're going to sample very small, tiny stress element on the shaft. So if I sample one small, tiny stress element like this on the shaft surface, square surface, I can take it out and examine how much of this, how the stress will distribute on this stress element. So if I rotate the left-hand side to the clockwise, then this stress element will receive the stress going to the right. I'm going to say it's tau. Okay, tau. And then on the right-hand side, the torque T is counterclockwise. So if I rotate this counterclockwise, then there will be stress going to the left, to the left right there. So tau is going to that, going that way. So that means if you see this stress element, there is a shear stress going in opposite directions. So this basically will cause the shear of this stress element. But one thing you need to remember is, if the stress acting on this opposite directions, this guy may rotate if there's nothing else. If there's nothing else.